Before 2017, sequence models like RNNs were powerful but slow. The transformer introduced a new way to process sequences, fundamentally changing how we build large language models today.
And it's all thanks to this paper, right? But I remember our previous cases, hashtag TCM123005 and hashtag TCM213002, where we talked about attention already. What was so revolutionary here?
Precisely. The field was dominated by recurrent neural networks, which process data one step at a time. This created a bottleneck for training speed and model depth.
So models had to wait for the previous step to finish before starting the next. That's inherently sequential, like reading a book word by word.
Exactly. This paper's title, "Attention is All You Need," isn't just catchy. It made a bold claim. We can ditch that sequential processing entirely.
That's a huge departure. To say attention could replace the entire architecture for sequence models seems like an enormous leap.
It was. The transformer proposed a new architecture based solely on attention, completely removing recurrent and convolutional layers. This was the game changer.
So no more step-by-step processing. But how does just attention manage to understand the sequence without a built-in sequential mechanism?
That's where parallelization comes in. Because each part of the input can be processed simultaneously, transformers are significantly faster to train than previous models.
So instead of reading word by word, it's like reading every word on a page at once and understanding their relationships simultaneously.
That's a good analogy, Maya. We explored the transformer's generalization in STCM123005, showing how this attention-centric design works for text and even for images in STCM213002.
So the core idea is that by focusing on relationships through attention, it becomes a universal tool for understanding complex data.
Let's dive into self-attention. Imagine the sentence, "The animal didn't cross the street because it was too tired." What does "it" refer to?
For us, it's clearly animal. But for a machine, it could technically refer to street as well. It needs context.
Self-attention provides that context. For each word, like "it," we create three different representations: a query, a key, and a value vector.
So every word gets these three distinct roles or perspectives when the model is processing it.
Exactly. Think of the query as what you're looking for, the key as what's available to be found, and the value as the information associated with that key.
So when it is the query, it's asking, who am I? And the keys of other words are offering answers.
Precisely. The next step is to calculate a score for how much each other word's key aligns with our current word's query. We do this with a dot product.
The dot product measures similarity, right? So a higher score means that word's key is more relevant to my query.
That's right. After the dot product, we divide the scores by a scaling factor, the square root of the key vector dimension, to stabilize gradients during training.
So this scaling isn't about interpretability, it's a numerical trick to make the learning process smoother.
Then we pass these scores through a softmax function. This normalizes them, turning them into probabilities that sum to 1. These are our attention weights.
This makes sense. Now I have a clear distribution of how much attention it should pay to every other word.
Finally, we multiply each word's value vector by its corresponding softmax score and sum them all up. This creates a new context-rich representation for our original word, it.
So it now contains a blend of information from animal, street, and every other word weighted by how relevant they are.
Crucially, this entire self-attention calculation can happen independently for each word in the input sequence at the same time. This is the core of the parallelization.
Ah, so the its query key value calculation doesn't depend on the animal's final output, only its K and V inputs, which are also being computed in parallel.
That's the key distinction. While the calculations within self-attention involve interactions, the overall process for each token is not sequential like an RNN.
So it's not truly independent paths, but more like a highly interconnected, simultaneous calculation, rather than a step-by-step chain.
With this mechanism, the transformer learns rich contextual embeddings. But what if we want to augment this internal knowledge with external facts, especially for very large models?
I see where this is going. We've talked about retrieval-augmented generation before. Now we're going to see how it integrates into the transformer itself.
In TCM 153004, we covered RAG, or Retrieval-Augmented Generation. Today, we're looking at DeepMind's Retro, or Retrieval-Enhanced Transformer, which takes that idea to a new level.
I remember RAG as grounding LLMs in external knowledge. Is Retro a specific architecture for RAG, or does it change how the transformer fundamentally uses retrieval?
Retro is significant because it showed that much smaller models could achieve performance comparable to models like GPT-3 by intelligently querying external information.
That's amazing. It suggests that simply scaling up model size isn't the only path to better performance. Efficiency matters.
It addresses a key challenge. Large language models encode all their knowledge in their parameters. This is inefficient for factual information, which is constantly changing.
So LLMs become expensive, static encyclopedias. They struggle with new facts and can hallucinate because they're relying on memorized data.
Retro tackles this by incorporating information from a database, freeing the model's parameters from storing vast amounts of factual knowledge. Think of it as outsourced memory.
Like giving the model a real-time internet connection instead of forcing it to remember every single web page.
Mechanically, Retro works by augmenting the input sequence with retrieved information from a database. This happens before the transformer processes the input.
So it's like adding extra context right at the beginning, guiding the model with relevant facts before it even starts generating a response.
The input prompt is first converted into a sentence embedding. This embedding acts as a query to a large database, looking for the most relevant text chunks.
So the model asks, based on this prompt, what facts should I retrieve? And the database returns the closest matches.
The most relevant chunks, often called neighbors, are then literally prepended or interleaved with the original input prompt. This combined sequence is what goes into the retro transformer.
So instead of just the prompt, the model now sees the prompt plus a few paragraphs of relevant information it retrieved.
But it's more sophisticated than just concatenation. Retro has specialized decoder blocks that used chunked cross-attention to integrate the retrieved information throughout the generation process.
So it can dynamically look up facts at different stages of generating the output, not just rely on what was added up front. That's a deeper integration.
Precisely. This deep integration means the model doesn't need to remember as much. Its attention mechanism can efficiently access external knowledge when needed.
This dramatically reduces the model's size and makes it more adaptable to new information. It's truly a smarter way to handle world knowledge.
From a revolutionary architecture that enabled parallel processing to a refined system that leverages external knowledge, the transformer continues to evolve and surprise us.
I'm Maya. Thank you for thinking this through with us.
I'm Arjun. Another idea in 3 hours. Take care of your mind.